One.
Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome CARLA FARSI from the most beautiful city of Boulder in Colorado, the heart of the Rocky Mountains. And she will rock us to the spectral triples and their geometric limits. CARLA, it's all yours. Take it away.
Thank you so much, Piotr, for the invitation and the kind introduction. Indeed, I want to speak on spectral triples and their geometric limits, and mostly in the framework of La Trémolière, who devised a distance for a class of spectral triples that he called metric spectral triples. And since this talk is rather long, I'm gonna give plenty of overviews of La Trémolière's theory on metric spectral triples, and then I'm gonna give some applications, not just the ones that are mentioned in the titles. Well, actually in the title is generically said geometric limits, so they all qualify for that title. But you know, applications that we have carried out in several papers joint with La Trémolière and also other people, which I will mention as appropriate. So let me...
CARLA, if I might wait, there is one mysterious person whose name is PS, and I suspect that it might be Frederick. I don't know, although these are not his initials. And if you don't mind, I immediately have a question. What is your second name?
Oh, my second name is Emilia. That's you know, a second first name is like, you know, in Italy, well, in Italy, I mean, that was the name of my grandmother.
Okay.
Emilia. So that's what it is. That's
very beautiful. Very beautiful. Thank you.
Yeah, thank you so much for this kind question.
I'm very much attached to my middle initial, so I couldn't resist the temptation. Sorry about it.
Right, I can explain you later after the talk in more detail. So, NC means non-commutative. Any other questions on notation on the first page?
I see La Trémolière is correctly written, so we are very happy.
Thank you. Yeah, he's one of the organizers, so I thank all of the organizers for inviting me. So, okay, let's see if I can change. Yeah. So the main ideas. This is a slide that kind of gives an overview of what I'm gonna do. The main ideas are the first couple of slides. So why we are doing this and where we're coming from and etc. That would be the first part, the very first part of the talk. Then I'm gonna go and do the details of many of the results. And I start by introducing the quantum compact metric spaces, which were first introduced by Rifo. They also were studied by several other people, but the take on it that I'm going to present is the one, of course, of Frédéric La Trémolière, because he's my collaborator, and we use that framework. But definitely, many people have contributed to this area in the world of sister algebras and also operator systems, which is a big area that has been developing very fast. And Kohn and von Sucherkamp were key to that area, to the development of that area. Although the original definitions were already introduced by Rifo in a more general context. So then I'm gonna go over these metric spectral triples, and then I'm gonna talk about some results that we did derive on spectral triples. This is quite old, almost 10 years old work, but you know, I I decided to give an extensive overview of several results in this area. And this result with Gillespie, Julien, Kang, and Packer doesn't really have, is not really strictly connected to the metric part of the spectral triples. They're just general spectral triples, but they are very interesting, and they are related to the spectral triples of Pierson-Belizar, which we adapted to the graph situation. I mean, we really use their spectral triples. And now with Andre, we are doing some calculations of these tensors on these spectral triples. I'm not going to talk about that work in progress as much. I just wanted to say that. Then I'm going to consider isometry groups of spectral triples, which were introduced by Conti, Roberto Conti, and maybe others. And in particular, we did compute with Roberto some special cases of these isometry groups. They're usually quite hard to compute. And we also computing them together with Frederic down here at the covariant bridge builders in some special cases of inductive limits. This word bridge builders or covariant bridge builders is a key concept in this area, because there are ways to show this convergence in La Tremolaire's framework. And first, what happens in that framework, first you show the convergence at the level of the quantum compact metric spaces associated to the metric spectral triples. I'll give more details on this later. Now this is just an overview. And then you pass to the actual convergence of the spectral triple, which means you add in an additional convergence properties. So these bridge builders, in the case of an inductive limit, they apply to the case of an inductive limit, allow to show this convergence La Tremolaire style. And the covariant bridge builders means there is also a group action that you can take into account. And so in this paper that is associated to this covariant bridge builders, in that case, they were applied to inductive limits acted on by a group in a suitable manner. I'm not saying all of the hypotheses, of course, here. And that kind of led us to take an interest in group actions, and that's how we got to the final result of this overview, this collapsing result, in which we have some kind of G-principal bundle, which in the easiest case is commutative, in the more complicated cases, like the ones introduced by Darbowski and Andrei Sitars, is non-commutative. And of course, there has been several other applications and developments since their introductions. And in that case, we have a group action, and in what we do in the paper with Frederic is to make like the vertical part collapse. So it would be a collapsing result in that sense, in the sense that when we make the vertical part, in quotes, collapse to zero, meaning we really make the metric collapse to zero. That's what it means. Then we have the associated limits of La Tremolaire style for these metric spectral triples to converge to the spectral triple on the base. So it's like if you think of the case of a principal G bundle on a manifold with all the suitable hypotheses, the spin structure is preserved. You know, you need a bunch of hypotheses. Then what happens is that the spectral triple on the principal bundle manifold will converge as the metric on the fibers ring to zero to the spectral triple on the base manifold, that being the general idea. Then there is some, you know, kind of details that need to be sorted out, some technicalities, as it is always for any result. So this is the main ideas that I'm going to talk about, and the main layout, and is the layout of the talk. I don't know if I will get to cover all of the details and all of the slides that I prepared, because I prepared quite a lot of them. You know, I was trying to get into the 90-minute mood. So I don't know how much of it I will cover in the end. But this, you know, even if you don't get all of the details and all of the cases, this is definitely the overview that you should keep in mind. And there are papers, many of them published, some of them still preprints, that these results are backed up by. So you can go and look up all of the papers. They're definitely all available on the archives. So you can go and deepen up whatever aspects you are interested in. And of course, in the papers, there is more details. Okay. So let's see here. What is the way to change? Okay. So as I said, the first thing I was going to do was this outline the main ideas underlining this work. And as I said, the framework we're going to use is the framework of quantum compact metric spaces on state spaces of unit or sister algebras. Riffel introduced them first and in more general context, but we stick to this case because that's the case that is suitable for the spectral triple applications. So what we are going to do, now I'm going to say more about that last part of the presentation that I did not give too many details on. You know, we are going to go do the generalize the Gromov-Hausdorff convergence of spin manifolds to a smooth spin limit. Well, of course, there are other cases in which the limit is not smooth and is still Gromov-Hausdorff convergence, but I mean, we have to, you know, start somewhere. So we had to put definitely lots of hypotheses, and the spin hypothesis is definitely something we want to put because, you know, we want to have a Dirac spectral triple. So we needed that. Of course, one could try to generalize it if one uses a Laplacian type spectral triple, but we didn't do any of that. And you know, these generalizations probably are possible, but they require lots of technicalities. So it might be context for future work, but we don't have any results right now as such. And so we want to generalize that limit on of convergence in the Gromov-Hausdorff case. In that case, they also have bounded volume, you know, they have a bunch of hypotheses, to the non-commutative context, and in particular to the context on non-commutative principle G bundles that were introduced, I believe, by the Borowski-Sitars, and for G equals the circle or T to the N. And then what we follow more closely is the presentation of Schwiger and Wagner that wrote several papers on free actions of Elwood type, and there would be this, what I call these non-commutative principle G bundles. And they also have a construction for spectral triples. They start from a spectral triple on the fixed point algebra, and they construct a spectral triple on the whole algebra. So we do use it for the last results I'm going to present, definitely that framework of Schwiger-Wagner, that particular framework that is very suitable for what we want to do. Okay, so that's what I was saying here. We do this free action in the sense of Elwood. I'll define it later. I don't want to do too many definitions in this introductory part. And then we do this in the non-commutative case, and we have various examples that this applies to. So this is relative to the last part of the of the talk, the non-commutative principle G-bundle part. So let's start with the quantum compact metric spaces. I know many of you might know this, but I have to start from the beginning. And the pioneering work, as I was saying before, was done by Rifo in several papers. And then Frédéric generalized this to the setup of spectral triples, which is what we are really using in this talk. And there were Kerr also did some work. I don't know if it was at the same time as Rifo or not, but they definitely quite early. Lee did several wrote a paper at least, maybe 2 papers on some cases of these limits. And then, as I was saying before, the operator system setup was recently developed, started by Kohn and von Suchelkom, but then it definitely picked up and was considered by many others, and it is still definitely in development. So we're not going to use these more general frameworks like Rifo or the operator systems framework. We just follow La Tremolier's definitions for the sister algebras case, because as I said before, these apply to the spectral triples that we are considering. So that's why we're using these definitions. But definitely there could be more general frameworks in which these similar definitions apply and have been developed in the literature. So, let's see. Okay. Here I more or less said all of this, and we are studying, at least in the last result, these properties of the Dirac operators on these bundles. And in the commutative context, there were results of Fukaya. Those were like the first results that was not in the Dirac context. Then Amman, Bear, Lot, Roos, and many others. And in the non-commutative context, there has been lots of results besides the ones I've already cited, because these principal bundles results are related to factorizations. I mean, that how exactly they are related is still a question of debate. And I mean, usually for us, meaning for Frédéric and myself, now I'm speaking about this last work, we haven't been able to really adapt our methods to more than the Schwiegen-Wagner context. The Schwiegen-Wagner context is a special case of these factorizations, but there are more general ones, this Kachik and the Mesland, and then the Van Suchelkom and Rennie. I mean, Brain, there is lots of people. I might have forgotten some, unfortunately, but they do factorizations of KK elements in several hypotheses and contexts. For us, since we were using that spectral triple framework and so on, we were not able to duplicate these limit results in those factorization contexts, except when they would arise, like in the Schwiegen-Wagner context, in which there were spectral triples metric spectral triples representing that. I mean, yes,
may I ask? So there is a question.
Sorry, I didn't see the
reason. From Adam. But before we let him ask his question, I have a simple, stupid question. This is Jens Pod you have in mind, or is it just a typo, or is it somebody I don't know?
Oh yes, CAD. Sorry, CAD.
Okay.
CAD. Yes, okay. It is a typo, definitely.
Okay, just to make it. Adam, ask a question.
Yeah. I'm sorry about that.
No worries. I just want to make sure that it's not somebody new.
Yeah. No. Cube probably would have with the needed to be cited to, there is lots and lots and lots of people there. Yeah.
Of course, yes. I know
So
this work of
sorry, I
Nesla.
didn't. Yeah. I misspelled that, sorry.
So
Yeah.
Yeah. How about Adam? What's your question? Sorry, I didn't see you raise the hand.
My question is about this convergence of eigenvalues of Laplacian. Do you mean that they converge also in some sort of Hausdorff distance, or just you order?
Yeah. I mean, that was proven, in this, of course, in this classical contest, that was proven by Fukaya, Mana, Mambar, all of those other people. The convergence of eigenvalues was already proven. So what we had was the convergence of these spectral triples as such, and that will give us the convergence of the functional calculus as well. The convergence of eigenvalues was already proven.
Okay, but still,
classical context.
Sorry, but still, I'm not quite sure whether I understand this convergence in the right manner. So, since the spectrum of Laplacian is unbounded, so you cannot
correct.
define a convergence in Hausdorff distance as the whole sets. So, what do? You order eigenvalues with increasing.
Yes, you order eigenvalues and show that, say, the jth eigenvalue will converge to the jth eigenvalue.
Okay,
The
that's
jth eigenvalue on the, say, we call the top manifold M, the bottom manifold, for us, they're all manifolds. The bottom manifold Q. So the eigenvalues lambda J of M will converge to the eigenvalue lambda J of Q.
Okay, thank you.
Yeah. And you can look, more detailed estimates and results in these papers. But yeah, that's what the convergence is like. So I don't see any other raised hands.
No, please go ahead.
Now we have a very, very basic definition. So, I was not quite sure who was coming to the talk and so on. So I just started from the basic definition. So for us, really, the convergence of eigenvalues and the convergence of the functional calculus is more like a result that follows from the fact that there is convergence at the level of spectral triple in this metric that La Tremolière devised for metric spectral triples. So as far as I'm concerned, I am not a specialist on convergence of eigenvalues, or, because all we did was the convergence at the level of spectral triples, and the fact that there is other convergences implied by that is a consequence of the paper of Frederic in Math and Allen about the convergence of spectral triples. So our result did not concentrate on how to show the convergence of the eigenvalues in particular. It was just concentrated on showing the convergence of the spectral triples, of the metric spectral triples that arise. So in order to define a metric spectral triple, we need to define what a quantum compact metric space is. Of course, there is a little bit of notation to be discussed. Quantum compact metric spaces, Frederick's label, Frederick's way of calling these spaces, Rifo, who was the first to introduce them, called them compact quantum metric spaces. So if you go to the literature, you might have, a little bit of translating to do, like from Polish to English, but it's easier than that. So, what you have is a unit of sister algebra and a semi-norm, usually on the self-adjoint elements, at least in this case of sister algebra. I don't want to do the order unit space, which is the most general case. And in this case, we have that, we have this semi-norm L defined on these self-adjoint elements, and you call it a quantum compact metric space when L is 0 only on the constants, and then you require that the associated Monge-Kantorovich distance, which is this a distance induced on the state space, this S of A means the state space of A, by this formula, which is a famous formula, I believe, metrizes the weak star topology, meaning induces the same topology as the weak star on the state space. And it also, because you need some other properties to show additional properties, like, you know, we all mathematicians do, you need this Leibniz inequality as well. So once you have this structure of quantum compact metric space on this state space, and I believe here Richard did some work on the diameter being finite and so on. So I invite you to look at that paper of Richard and Cute. And so we have this structure on these self-adjoint elements of this unit of sister algebra that the associative Monge-Kantorovich distance induces the weak star topology. We call this a quantum compact metric space, quantum compact, and so it's compact, it will have finite diameter in particular. So that's what we are starting with. We have also, as I said, the Leibniz inequality. And this is the main tool that we're going to use to construct our so-called metric spectral triples. So a spectral triple is going to be metric when the Cohn's metric induces the weak star topology on the state space. So instead of using a general L for a metric spectral triple, we use for L the norm of the commutator, dA, where D is the Dirac operator of the spectral triple, and A is an element of the algebra. So for, for this particular L, when we are using a spectral triple, we don't use a generic L, we use a particular L, which is given by the norm of the commutator. Of course, this is a classical spectral triple, so normal commutators are bounded, at least for a dense subalgebra. Okay, so we define now some of the tools for La Tremoliere's construction. As I said, it was originally introduced by Riffel, so these things are not really that new. And quantum isometry, you know, using isometries between these objects, and a quantum isometrist has suggested isomorphism from the two sister algebras such that the L associated to the second one is equal to the inf of the L associated to the first one on the fiber. So that's the definition of a quantum isometry. And this generalizes the definition of isometry. Now we're going to define this is really a very strong concept, very useful and important concept, is the definition of tunnel between quantum compact metric spaces. Of course, here there is a little bit of notation to take into account again. Is it tunnels or is it bridges? Well, tunnels and bridges, as defined, are like one dual of each other. So we'll see in a second what I mean. Okay, and I mean this, by the way, is in Colorado. And I mean, you should look at the structure. Here there is no arrows, but, you know, a bridge is quite similar. I should have a picture of a bridge here. Okay, maybe I did. Here we are. Well, sorry, still another bridge from Colorado. I couldn't find any others. But the point is that in tunnel, the arrows will go up, and in a bridge will go down. So these concepts of bridge was already defined by Riffo. These concepts of bridge and tunnel, actually, this is tunnel, the other one was the bridge. Sorry, one goes up, one goes down. I think I might have said the wrong one by mistake. So these tunnels and these bridges are one dual of the other. You know, in one, the arrows go down, in one, the arrows go up. And La Tremolière uses tunnels because in his theory is able to show a little bit more. But really one could use bridges, you know, with the arrows going up, and every tunnel induces a bridge. So it's not clear if one could do the whole theorem with just bridges, which usually are a little bit easier, but I don't want to get into too many technicalities. We use in tunnels because that's what the cleaned up theory, well, cleaned up in the sense how Frederick framed this theory. I mean, Riffel and so on were totally clean theories. They were just different. But La Tremolière prefers to use this because it can prove a little bit more when it comes to completeness and other properties. So we're going to use his description, what I said before, these quantum isometries, and this is going to be a tunnel. And this is what would be the main point for proving many of these convergence results, because in order to show that two of these objects are close, like say if I want to show that the ALA and the BLB are close by epsilon, you know, are epsilon close in this theory, what you do, you find that D, like a tunnel that fits like that has the so-called extent less than epsilon. Of course, I haven't defined what the extent is, but given any tunnel, there is a number that you can define, which is called the extent of that tunnel. And those two, LA and BLB, are going to be epsilon close if that so-called extent is epsilon. So what you do in order to show convergence is build these tunnels that are that show epsilon closeness for generic epsilons, and so that will show, you know, as epsilon goes to 0, that the limits is the same. The limit of the first is the second, or that the two limits of the first and the second are the same, depending in which situation you are. But that's the main tool. This is at the level, though, quantum compact metric spaces. If you want to do it at the level of spectral triples, what you do to show convergence is show convergence at the level of the underlying quantum compact metric spaces. And then after you've done that, you also show some additional condition that comes from a semi-group action e to the TD, where D is the Dirac, so that everything matches together nicely, and that gives you convergence at the level of the spectral triples as well. But this part, the convergence of the quantum compact metric space underlining the spectral triple, is the base, the foundation of the theory. Without this, you don't even start. Okay, so here I can give the definition of the extent of a tunnel, but perhaps I might not be as thorough because I want to get more to the results. This is very classical theory. More or less, the extent of a tunnel measure the Hausdorff distance between the state space of SA when you embed it and the space of SB. This is a little bit different. It's not quite the same, but it's very close. Once we have this, we have a reversed diagram with the arrows going the other way when we look at state spaces, because, you know, they go the other way. And then intuitively, it's not exactly that definition, but it's the idea is that you take the state space of A, you put it in here, the state space of B, you put it in here, and you measure the distance in there of these two. And if that distance is small, that's when the extent is small. It's more or less that. It's just a technical variation on that. So that's how we do it. The extent of a tunnel is what I defined. And then with this, you can prove convergence at the level of quantum compact metric spaces. So here is the picture I've already shown you. And here I'm going a little bit more into that discussion about bridges versus tunnels, but I'm not sure it's really worth much expansion right now, because these are just variations on the theory, and what I want to present more are like the results rather than some technical variations of the theory. But it's an interesting question if one can do everything that one can do with tunnels, with bridges, and vice versa, and so on. And it could be that somebody at some point is going to give an answer to that.
But bridges seem to be easier, no?
Exactly. That's why, people are tended to try to use bridges. In fact, if you look at many papers, like in operator systems and so on, but not only in operator systems, they use the bridges, and RIFOL use bridges.
Yeah.
And yes, bridges are easier, but it's not clear that you can do absolutely everything with bridges. You might. So, I mean, anyway, since La Tremolière, who is my main collaborator in this work, uses tunnels, definitely he developed his theory in terms of tunnels. Definitely it's worth, for me to stick to tunnels. But yes, it might be possible that you can do everything with bridges.
Okay.
Yeah. It's not proven that you cannot do it. So
There's no-go theorem, yes.
exactly. So, okay. So this is the point of using tunnels, because this, and that was, as I was saying, that was proven by La Tremolière, which, is on the organizing committee. And he said he couldn't be here, unfortunately, because he teaches at 10 at Colorado time. So the dual propinquity, which is, what's this dual propinquity? Is this distance that I defined in terms of extents of tunnels. That's what this dual propinquity is. Sometimes another notation thing, sometimes it calls it the dual propinquity, sometimes it calls it the propinquity. So you have to be a little bit careful. It changed notation as time went by. But so, when you read one of his papers, make sure that you know exactly what it means in that particular paper. But the point of La Tremolière switching to tunnel is that it could prove that this this distance that I just defined, he called it propinquity, so let's just call it propinquity, is a complete metric up to full quantum isometry, meaning if two spaces at distance 0, then they are isometric, in the sense of full quantum isometry means invertible ones. That's what it means, full. Okay, so as far as I know, this result has not been proven for bridges, but that, doesn't mean it's not true. As I was saying before, it means just it hasn't been proven. And so that's why in this paper, La Tremolière settled, I believe, on this, because he could prove this result, which is an important result. Okay, so now we go. I'm not even gonna give the definition of spectral triple, I know, for the audience, but sometimes, maybe somebody looking at this talk online or something might. Of course, I do very quickly. you have a sister algebra. Usually you have a dense subalgebra specified, and then you have an unbounded operator on H, and on a Hilbert space H, and you have a representation of the sister algebra on H, and you require a few properties, but in particular, this property of the commutator being bounded is key to us because, as I told you already, the lip norm, I didn't call it lip norm, but that L could be called lip norm. That L is, in the case of a spectral triple, exactly the norm of this commutator d pi of A. So this is definitely a crucial property for us. Okay, so again, that's repeating what I was just saying, but at least it's written down. Okay, let me put this in a side. I don't want it in the middle. Yeah, I don't know why it's kind of covering this less or equal than 1. Anyway, this is the definition of the cone metric, which, as I told you already, was the Kantorovich metric associated to this L of A being the commutator dA in the case of a spectral triple. So we call this the cone metric. Kohn introduced it, that's why the name. And I told you already, but now it's written down. A spectral triple is called the metric according to, here is another question. Just let me say this for a minute and then I will entertain the question. A spectral triple is called metric if this distance induces the weak star topology on the state space of the associated sister algebra. For us here today, all the sister algebras are going to be unital, even though I don't know if I wrote it anywhere. One could potentially generalize this to the non-unital case, and I believe Frederic might be working on something like that, but in this talk, only unital sister algebras are considered. Yes, Adam.
Yes, just a quick question. Pseudo refers to the fact that this distance could be infinite, yes?
Yes, yes, but we want it to be finite because we want it to be the weak star, the distance. We want it to be a distance. So it could be infinity, but in our cases, we want it to be finite. So in the spectral triples we call metric, we want it to be finite.
No, but I think that inducing weak star topology is a different thing. It's related.
No, I understand, but we want it, the above distance, we want it to be a distance.
Okay.
So it's an additional, I agree with you, it's not the same, but it's an additional requirement that we make that it is a distance in our case.
Yeah, so maybe to put it in another words, you can have something which is like a pseudometric, so you allow infinite distances, but still it could generate the same topology since generating topology.
Yes, but we do not allow that.
About
in our definition, I didn't write it completely. This could be, totally agree with you, it could be induces the weak star topology when this is infinite, but we do have it finite as well. So, we also ask for it to be finite in the cases we are considering.
Okay, I understand. Thank you.
Yeah. And
Carla, may I ask a stupid question? So imagine there's sister algebra A is commutative and unital, okay? And say you have some standard Dirac operator.
Yeah, now, then the metric is the metric on the manifold. That has been shown by, for example, Park and maybe even Kohn. Park for sure. I don't remember his first name, but there is a paper, I believe, in the proceedings of the AMS. So in the case of a standard compact closed manifold, this spin, all of the hypotheses, it is the standard metric on the manifold. Because the state space is the pure states are the points on the manifold, and the metric, the cone metric, is not a pseudometric in that case, it's a metric, and it is the distance the standard geodesic distance on the manifold.
Thank you so much. That's
No,
exactly
that's a good point. That's a good point. Yes, I maybe should have also said here, we require the above pseudometric to be a metric, to be a distance, so finite. So that's an additional requirement.
So also it is true that this commutator is just a gradient, yes, in this commutative case.
Yes, that's correct. That is correct. In the special case of a manifold, etc., yes, it is the gradient. That is correct. And that's proven maybe even in the book by Landi now, but oh, sorry, here. I'm trying to make it so it doesn't cover the slides. Or maybe put it here. Okay, no, then I cannot. Well, you should alert me questions now. Sorry, guys. Okay, now it's there. Yeah, so yes, that is correct. That is correct. It has been proven. It's not a long proof, but it requires a proof. And might be it is also in some paper by Cohn or somewhere by Cohn. I don't know. But definitely it's proven in a paper by Park, Efton Park, I believe. I believe in the proceedings. I cannot look it up right now because I have the screen busy with my slides, but it's if you know, it's definitely there, proven in all details. And I believe in the book by Landi. Yeah.
I think that also one can find a proof in the notes which were written during the lectures of Joseph Varily in Warsaw. Piotr.
Yes, I think it's also in Varily's book. So I would imagine it would be in the notes by Varily. Yes, yes. Yeah, that it's in several places, definitely in several places. So, okay, now let me talk about, since this has raised some interest, let me say something about this metric, which is not always a metric, and cases of this pseudometric and metric. So I'm gonna talk a little bit about this construction. This is not part of the G principal bundle, part of the talk. I will come back to that later. In this, there is this famous spectral triples of Pierson-Belizar that are for ultrametric Cantor sets. What are ultrametric Cantor sets? They are Cantor sets whose distance satisfy a stronger form of the triangle inequality, like instead of distance xy less or equal distance xz plus distance zy is less or equal than the max of those two distances. So it's a stronger form. And Pierson, in his thesis, studied these ultrametric Cantor sets, and in particular, he gave spectral triples of them joint with his advisor, Belizar, and then they published a paper together. So there is a lot one can say about these spectral triples, and a particular thing to say is that the spectral triples are non-metric in general. If you just, I don't want to get through the definition of them because it will probably take me another half hour. But in this case, one can see all of these behaviors, like the metric being infinity or the metric being finite. And in particular, Kellendonk and Savignan studied a special case, and Kellendonk-Savignan is down here, a special case of these Pierson-Belizar spectral triples in which the metric is always finite. And not only they proved it was finite, the cone metric, it induced a weak star topology, and also they found a formula for this metric. So if you are interested in seeing an example which is not the standard manifold Dirac operator type of setup, this is a good one, this Kellendonk-Savignan spectral triples. And in joint work with Conti, we studied the isometries of the spectral triples of this special type of Pierson-Belizar, that is of this Kellendon-Savigny type. Since the ultrametric Cantor sets via the Michon constructor are shown to be isomorphic, well, isomorphic, I mean, homeomorphic to the boundary, meaning the infinite path, that's what I mean by boundary, of a weighted tree. In particular, the case we studied was a weighted binary tree. So then what happens is that these isometries turn out to be isometries of the associated tree, practically. So it's a really interesting interconnection. There is an interesting interconnection between the tree that represents the ultrametric Cantor set via this Michon construction and the spectral triple and its isometry group. Of course, I haven't even said what an isometry of a spectral triple is, or isometry between two spectral triples. I guess I leave that a little bit to your imagination. So let me skip this, this result that we did together with Gillespie, Julien, Kang, and Parker, which was like an adaptation, if you want to have an idea, an adaptation of the Pierson-Belizar spectral triple to the context of K-graphs. We did not construct spectral triples on K-graphs, just this was done not on K-graphs, but on graphs. This was done by Mesland, Goffin, at least on the case of graphs. And you can look them up. We did not construct that, but we adapted this Pierson-Belizar construction to fit into the infinite path space of the graph, or the K-graph in the case of the K-graph. And then there were some formulas that came out of that, and we had some fun computing certain invariants. And in particular, we linked it to wavelets on the sister algebra generated by the sister algebra of the K-graph. So our main goal here was the link of the wavelets that we had on this particular setting to the eigenspaces of these Pierson-Belizar spectral triples on the infinite path space associated to the graph, not the whole graph. So we did not have wavelets, spectral triples on the whole graph. But we had this link with wavelets, so that's what we did in this work. Okay, here we are, the groups of isometries. I was saying we computed the isometries of those special Kellendon-Savigny spectral triples, but what are isometries? Well, there is actually different types of isometries. Perhaps one can define even other types of isometries. And these don't require the metric condition. So I am a little bit diverging from that theme of these metric spectral triples that are the ones you can compute the Latremolière limits. Right now, I'm just considering generic spectral triples. They don't need to have a con pseudometric, which is a metric. They don't need to have the con pseudometric induced the weak star topology or anything. They're just spectral triples. There is two definitions, and as I said, maybe more, but these are the two main definitions that Roberto Conti and his collaborators have been considering. The small group of isometries is, well, this might be the most computable because there is supposedly a unitary implementing the automorphism of the algebra on the representation. And then you ask for this unitary to commute with the Dirac operator of the spectral triple. So this is kind of a definition that it's a little bit easier to put your hands on because it requires to show the existence of a unitary with a commutator property. The other group of isometry could be just practically the group of isometries of the cone pseudometric or metric is a metric. So that is a little bit hard. I mean, we found it harder to put our hands on because it's abstract, you know. You have this generic metric on this state space. I mean, if A is nice, you might know the state space well, but if A is not nice, you don't even know the state space that well. And then you are just asking for the isometry of a certain metric, even if it is a metric and not a pseudometric, but still, I mean, it's not so easy. Yeah.
Sorry, Carla, is it really obvious that the small group is a subgroup of a large group?
I'm gonna give you a proof in the next slide. Let's see what Adam wants to ask.
Yeah, Adam.
Let me just go to the next slide, but let me see what the question.
Yeah,
Okay,
so I have a follow-up question. Is this a normal subgroup?
Oh, I don't know. Good question. Very good question. Yeah, I don't know.
No idea.
I don't know. In the case we have been considering, they were abelian. Actually, they were equal. In many cases, you know, because these isometry groups, believe it or not, they are not that easy to compute. By the way, here's the proof.
Okay.
Because, you know, the L is going to be the same when you put the, you know. So anyway, yeah. No, I mean, in the case, let's get back to this. You know, in the case what I done in this case is just this computation with Roberto and then another computation, but we never addressed that question, which is a very good question that Adam asked. Is this a normal subgroup? I don't know. I mean, right now, I don't have an answer. If I do get an answer, I'll let you know because it might even not be that hard. I just haven't thought about it. So I can't quite, I can't quite speculate at this stage.
And Adam, was the source of your question and observation that somehow alpha in the small group is a kind of inner automorphism?
Yeah, exactly.
Okay. Okay, so I understand why I asked this question. Okay.
Yeah, in the context, for example, for von Neumann algebra, there is this group of outer isomorphisms, which
exactly.
is
Now, it is possible that something like this has been already even written in some of Roberto's papers on this. We didn't write him, we didn't consider this, but I cannot say for sure. You know, I just don't know. That's all I can.
Okay.
But it is possible that Roberto has already considered this question and answered it. Or, you know, that maybe I take half an hour to go and look at these papers and I find the answer there. Or, you know, 2 lines. It's possible. I just don't know right now. That's all. By the way, there is a conference in Rome in honor of his 60th birthday, February the 6th, the 21st and the 22nd, I believe. Okay, but that's a very interesting question if has not been answered already. But okay, so let's get now to this computation of these isometry groups. In the case, okay, we already talked about this. You are an attentive audience. We already anticipated the first point. And then Rossi and Conti computed the Goffin-Meissner spectral triple on ON. I told you that Packer and all of other collaborators, we didn't do spectral triples on graph algebra such as ON. We just did the restriction to the of the Pearson-Balizard to the infinite path space. But as I was saying, Goffin and Meissner did do the spectral triple on ON, and I believe they also did Krunz-Krieger algebras extensions. Anyway, Rossi and Conti computed this small ISO group, and then Bassi and Conti computed some groups of spectral triples associated to some AF algebras. They have more for UHF. And then what I did with Roberto was the isometry group of those Kellendon-Savignan spectral triples, that is the ones that I was telling you they are Pierson-Belizard with special conditions so that they become metric and nice. We could do it because of the fact that Kellendon and Savignan had already computed the metric, the cone metric, and so that definitely helped.
May I ask you, what are Bogoliubov automorphisms of the cones algebras?
I'm sorry again, I couldn't catch your question.
What are Bogoliubov automorphisms of the cones algebras?
Well, just Google them.
Okay. Okay.
I mean, that's not my work, is their work.
No worries, no worries.
Types of, certain types of automorphism. I hope I didn't misspell it. Okay, let's proceed more to what I want to concentrate on. There is still another half hour, so I should be able to give you a good overview. Good money for your hour and a half. So here, so what we want to do now is what we did in, so I said what we did with Roberto here. That's one of the points I was supposed, oh no, sorry, got the wrong way. Here, the isometries of the Kellendon-Savignan spectral triples on the ultrametric Cantor sets, you know, the Kellendon-Savignan type. And they both came out to be isomorphic to Z lower 2, the group on 2 elements. That is, the automorphisms of the binary tree identity and the one that switches everything over, like 0 goes to 1 and 1 goes to 0 if you do the tree, if you call it with terms of zeros and ones. The flip, in other words. So that's what we did, and this doesn't have anything to do with La Tremolaire's theory. This was just done by a calculation, just by finding a specific unitary implementing what in the automorphism, and also using the fact we had the explicit formula for the cone metric in this case. So here, now we wanted to do a little bit more when we talked to Frederic, and we wanted to see that in case in which the algebra arose as an inductive limit, we hypothesis. I mean, we could do very little in the general case of just arising in the inductive limit. But with suitable hypothesis, we could do a theorem of the following type. The isometry group of the limit arises as the isometry groups of the limiting spectral triples, but many times we wouldn't get surjectivity. We just get that the inductive limit of the isometry group of the spectral triples will just embed inside the isometry group of the limit. We, you know, with very special hypotheses, we could also get surjectivity, but definitely not in general. So it's tricky, but we could get some limiting results of that type. Now, that is what we did with the isometry. Now let's come back to the Frederic La Tremolaire framework in more details so I can explain more results. So La Tremolaire, as I said, made this theory for using tunnels for quantum compact metric spaces, but then he extended it to many other things like modules over quantum compact metric spaces, star correspondences, dynamical systems, and so on. So if you look, there are several papers by La Tremolaire that expand the propinquity to this other setup, and this takes different names, the modular propinquity, you know, various variations. They're all quite technical, but the ideas are simple. You just extend it to these other classes. But the technicalities are definitely there, and you know, it's not such an easy extension. But the idea is, yes, we extend it to these other bigger classes, not just sister algebras, but all of these other objects. And especially important for us, metric spectral triples. So in the metric spectral triples case, like I was saying somewhat before, you take first the quantum compact metric space coming from the norm of the commutators, the L, and then you put on top of that the fact, you use on top of that the fact that that any spectral triple gives rise to a C-star correspondence between the algebra and C, the algebra you are doing the spectral triple on, and also you have an action of 0 infinity, which is e to the t Dirac, that being the t, and you put all of this together with lots of technicalities, you get the fact that you have this spectral triple metric. Yeah.
Sorry?
Yes. Don't see people. Yeah. Now let me see people. Yeah. Sorry. Yeah. Go ahead, Adam.
Yeah, I'm a little bit confused by this statement about the inductive limits of what? Of isometric groups, or
Where? Here in the slide or in the prior slide? Sorry, I didn't. Right now, I'm not seeing people. I didn't see when you raise your hand. I should
in the
try to.
previous slide?
The previous slide?
Yeah, the previous slide. You had the spectral triple, which is inductive limit of some sequence of spectral triples or
Yeah.
some system. And then you said something about this isometry groups, that those isometry.
Yeah, I'm going to expand on that later. What happens here is that we have an inductive limit of spectral triple in the sense of La Tremolaire's. So here I just wrote it, interwoven with the theory of inductive limits of spectral triple. So I did not give many details. What happens is that when we have an inductive limit of spectral triples, what does it mean? It means you have an algebra, which is an inductive limit of algebras. And then you have a sequence of spectral triples on these, say, AN goes to A, just to be, Then you have a sequence of spectral triples on these ANs, so one per each AN. And then these spectral triples on the AN converge, they are all metric, and converge in the La Tremolaire spectral propinquity to the spectral triple you have on this limit sister algebra. That's what I mean. This theory of La Tremolaire can be interwoven with the theory of inductive limits of spectral triples. Like you can consider this La Tremolaire spectral propinquity as associated to algebras arising as inductive limits of other algebras. So of course, that's not always the case. You need a hypothesis, because if you have an algebra limit of all the inductive limit of other algebra, it's not always true that any spectral triples you put on are going to give you the convergence in La Tremolaire sense. So to be able to do that, you need to put a hypothesis.
Of course, yes. That part is fine, but I had a problem with this isometry groups. Do you have a notion of Gromov-Hausdorff, this convergence of isometry groups? This is
Yes,
what
we do.
for me.
We do.
Okay.
I mean, La Tremolaire does. We do have a notion. We do say when two groups are close, and that's part of the theory. So yes, there is but I mean, I'll probably get to that, or if I don't get to that, I can send you all of my slides, and there is, or we can, after I finish with the talk, we could go to that slide. There is a notion, but all of those things are technical.
Okay, but there is a notion. Okay, so
there is a notion. There is a notion.
Yeah.
I might be able to get to that. Otherwise, it's definitely in these slides, so no problem. But there is a, we unfortunately, La Tremolaire's theory is very beautiful and encompasses many areas, but I mean, in its kind of building up. But there is a notion that La Tremoliere is able to combine with these other notions to make into a coherent theory. And that's how we do it in the paper on the isometries with Bassi and Conti. So this paper is the one with 4 names, Bassi, Conti, La Tremoliere, and myself. That's where we do combine La Tremolaire's framework with La Tremolaire's limits. So that's where you can see. I don't think we had done it at the level of isometries in any other papers, but probably one could apply to other examples besides these inductive limits that we consider there, this special case of inductive limits that we consider there. But so far, that's the only case that we've been treating.
Okay, thank you.
But yes, it's a good question. When can you apply? Is there any other cases you can apply? We've been discussing this some, but we don't have any paper that it's any close to completion on that. I mean, they take a long time and each case presents some difficulties. So, but that's definitely a very interesting question. Yeah. But I will say more about that hopefully soon. So this was the extension. The correspondence, you know what a correspondence is. So what do? We take a metric spectral triple and we set the correspondence associated to this, as I was saying, is between A and C, all of this data. H is the Hilbert space, Dn is this, sometimes we call it D norm. Of course, D norm is a good name. A is the algebra the spectral triple is defined on. LD is the usual LD, the norm of dA. I didn't rewrite it, but it has been, no, here it is. Norm of dA. C is the complex numbers, 0 is the 0 LD on the complex numbers. And then, let me skip this, it's not really that meaningful. So, for every spectral triple, which is metric, so we are assuming it has the property we said before, the cone metric is a metric and induces the weak star topology. We are putting on top of that construction that gave us the distance between two quantum compact metric spaces. Remember, that was given by a tunnel. And this D, of course, is the algebra associated to the spectral triple. This LD is the L of the spectral triple norm of the commutator. To make it into a metric tunnel, meaning tunnel of metric spectral triples, you have to add all of the structure. So it's easy if you just draw it like this. When you start doing these calculations, it's not as easy because you have to show that each of these maps is a quantum isometry. Then there is some kind of Leibniz inequality you have to prove. I mean, it gets complicated. But the idea is this. You just check that this type of diagram commutes, I mean, makes sense. And then that all of these maps that you defined are quantum isometries. And then you have that the so-called extent of this tunnel, this kind of upgraded tunnel, is the number you're looking for, like is the distance between the two given spectral triples. So that's the idea.
Sorry, do I see it correctly that this is like having a tunnel between bridges?
Oh my gosh. This is a tunnel. They're all tunnels. If you have a bridge, I suggest you first make it into a tunnel and then you try to apply here because
I see surjections I see 3 pairs of surjections. So I thought these were like bridges.
Well, I hope they're not, but they are what they are.
Okay, okay. So just a coincidence. Okay, okay.
Let's go back.
Okay.
Ah, here we are. This is a bridge going up. This is a
Wait a
tunnel.
second. Oh, so this is a bridge.
tunnel going down. So the tunnel goes down.
Oh, I'm sorry. Yes. Okay, I
That's
confused
okay,
it.
no
Yeah, yeah,
problem.
yeah. My bad. Yes, I confused the
Well,
terminology.
of course, you could reverse some of these because if you go to
Yeah.
the state phases, but let me, it's complicated as enough as it is. Let's not try to
Okay.
make it complicated. But yes, this is definitely a tunnel, but could be, I know, that one could redo some of La Tremolaire's theory in terms of bridges. I'm not saying it's not, even at the level of spectral triples. I'm not going to say it's not possible. But right now, let me just stick to this and, we'll do it with this way. But it might be possible. I think that's what you really meant to ask. It might be possible. But I haven't seen it, and it's probably complicated, but it's possible, and it might give an easier picture of this. It's possible. It's just, as I said, since La Tremolliere uses these and these give completeness, we'll stick to this. Okay, so that's the picture. And then what you're asking, which is not really reflected in the picture as much, is this action.
Uh-huh.
So it's not the action of the isometry group here, but it's close to Adam's question. It's not the action of an isometry. That has to be, let's not do it yet. Sorry, here. Let me switch off the phone so it doesn't ring. Okay, so what, one cannot really put that in the picture, but these are all the definitions of the terms involved. You don't need to worry about that at the level of the talk. But what we have is this action, and now we come back to Adam's question, is the action coming from a monoid, but the one we are considering here is e to the td, is not the one from isometry, but that's the same idea. So one can consider isomorphism, epsilon isomorphism from monoids, of course, if we want to get a group like the isometry group, you could do that, to another monoid. So, and this is exactly what Adam was asking by. There is a construction, and this is the construction for the distance that works. It could be that this type of distance was already present in some of Gromov's work. I don't know. I haven't really studied the history of this, but you can definitely find it in La Tremolaire's paper 18, which in 2018. So this is the distance, I think, that Adam was talking about. So one uses this, but not for the isometry group yet, but one uses this, and then by using this, one answers this question: how far are these actions? Which actions? Well, the actions e to the td type of thing, not, again, the isometry group. And so I didn't put it here, but one has a formula that practically evaluates these actions using those type of epsilon isos practically, and sees how these different semigroups generated by the Dirac operators are. And that's how one can get the convergence on the eigenvalues eventually, and so on, because one has not just this, which is, I don't want to say algebraic, but perhaps is a more algebraic construction, but one by putting in the requirement that there is that there is a, well, not really isomorphism, but isomorphism up to epsilon between the semigroups generated by the Dirac operators. Assuming that that is small, one can get convergence of the functional calculus and of the eigenvalues as well. And this is explained in detail in La Tremolier's paper in the Annalen, which is published maybe a year or two ago, or maybe in 18. I don't know if 18 is the archive date or the published version. Okay, so this is all of the framework. As a consequence of this theorem, you have convergence of the eigenvalues, like we were saying at the very beginning of the talk, like one eigenvalue, a limit of a lambda n converges to lambda. And the bounded functional calculus is continuous as well. If you want details, you can go to his paper. That's 23. So I guess that's a different paper than the one I cited before. This is the one on the convergence of metric spectral triples. Okay. Now, finally, we come to, in the last 10 minutes or so, we come to the, to the results. So we were supposed to talk about bridge builders and covariant bridge builders. So bridge builders are some special tunnels that one uses to prove metric convergence. When I say metric convergence, I mean convergence in the sense of La Tremolière. In the stock, that's all I'm considering. For the propinquity. So in the case of inductive limits, I don't know where I wrote it, but yeah, I mean here really it's in inductive limits cases. I didn't repeat it everywhere, but in this talk, in this slide, I'm only gonna talk about situations arising from inductive limits. Like an algebra is an inductive limit of some algebra, say an. I just take n to be in the natural numbers to make it simple. And associated, we assume there is an associated limit in La Tremolière sense of spectral triples on an to a spectral triple on A. And these bridge builders are a quick way to prove that convergence. So one has the situation with these spectral triples on the limit and the spectral triples on the factors. And by using these bridge builders, which are special tunnels, really, it's easier to prove this convergence. They really, use bridge. Now, every bridge gives rise to a tunnel. So as Piotr said at the beginning, or sometimes, bridges are easier. So yes, we do use tunnel because in the theory, it's nicer, it's a more general result and so on. But whenever we can use bridges is better because they're easier. So in this bridge build, so that's what this paper is about, the bridge builders paper. And then there is a covariant version in which we make it interact with these isometry groups. But these are technical results. And so, it's kind of probably at this point, it's probably easier to read the paper and try to figure it out if you really need to apply or to generalize it or whatever. So you have, this inductive limit of the ANs, but there is also a length associated with certain properties. And then this bridge builder is a morphism that goes from the limit, A infinity is the limit, yeah, here it is, to the A infinity with certain properties that practically make easy to construct a bridge. That's why it's called a bridge builder. And if you look at the literature, there are variations on this type of constructions, not the same, but some variations that people have applied to compute bridges. So once we have this situation, we applied to the case of certain inductive limits. And this type of bridge building can be souped up to give a convergence of the spectral triples when you do have spectral triples. You know, this first bridge building result does not have a spectral triple. It just has the quantum compact metric spaces, but you could soup it up and it does work. Okay, I'm not going to do the proof or anything because I want to give a few more of the results since it's only, I think, only 5 minutes left. So here we just, the main result was the main application was to the abelian group's limits of subgroups. So you take an abelian group which is not finitely generated, like for example, we had some examples here. Well, it's getting quite technical, but if you have like Z1 over P, that's a limit of the subgroup ZPN, Z1 over Pn, and then you can use the subgroups. Practically, the idea is that you have a big abelian group limit of subgroups that grow into it, and then you can prove the convergence of associated objects like quantum compact metric spaces or inductive limit spectral or limits of spectral triples. And this is the covariant version in which you have the action of this isometry group. That's what you think of having. But let me not go too much since there's only 5 minutes left. Let me go to the results on principal bundles. Okay, so collapse.
So here by collapsing, you mean like collapsing your fibers, right?
Exactly, Piotr. When I mean collapsing, what I really mean, collapsing is like a term that was used by Fukaya. So what he did in that kind of pioneering work, it was to take these Gromov-Hausdorff inductive limits of closed manifolds with bounded volume, I believe, bounded curvature, and then make them converge like Gromov-Hausdorff convergence to limit, and say, under certain hypotheses, then there would be convergence of the eigenvalues, for example. And he called that situation collapsing because an easy example would be when you have some kind of principal bundle, well, even easier, just a product, just to make it really, really. And then you are collapsing one of the two manifolds in the product. Of course, that's not an example that people would write up, but just to understand what we're talking about. So collapsing, meaning you take a principal G bundle, you make the fibers collapse, and G is a compact group. And you look what happens in the Gromov-Hausdorff metric in the classical case, or you look at what happens if you consider, for example, in the commutative case, the standard spectral triple on the bundle that converges, you hope, to the standard spectral triple on the base when you collapse the fibers, the metric on the fibers to zero. Okay, so that's what it means collapsing. So the point of this paper, the last one we have on the archives, is that we want to kind of make this collapse situation in subtotal hypothesis. Spin, we definitely have a hypothesis, a result on spectral propinquity limits, meaning what the idea to prove is that the metric spectral triple that one defines on the principal bundle converges in the spectral propinquity when the metric on the fibers tends to 0 to the standard spectral triple on the base. And this is true for the classical case of commutative case, but it is also true in some non-commutative cases, which the first of which were considered by Sitars and Nabrowski, but which were considered, as I was saying at the very beginning of this talk, by Schwiger and Wagner, which in this, with hypothesis of this free action in the Elwood sense, they considered, they did this, they constructed, given a spectral triple on the fixed point, which in this case of the abelian case would be on the manifold at the bottom, on the manifold and the quotient. They constructed a spectral triple on the whole bundle that restricts on the fixed point algebra to the spectral triple on the quotient. That's what they did. And so we used this construction, we took their spectral triple, and we made the metric on the fiber shrink, and we showed that that spectral triple on the big space, when the metric on the fiber shrink, which means in special cases dividing the Dirac operator on the in the vertical direction by epsilon, in that case what happens is that the spectral triple converges in the spectral propinquity to the spectral triple on the base. So this is kind of the main result, and that holds not only in the Schwigen-Wagner situation. We also had a more general statement, but the main application is that Schwiger-Wagner situation that applies to this special case of G-principal bundles that they were considering. So that's it in a nutshell, is the result. I mean, I do have more details, but I mean, I think the time is over, and it's really, you know, if you're really interested, just look it up, or, you know, try to plan a visit or whatever, you know. But I mean, taking, you know, talks are usually to give some ideas and to try to make people interested, and then you can go and look up all of the details in the papers. So I would just finish here.
Thank you so much, Carla. Thank you.
Yeah, thank you.
This was a very beautiful landscape full of bridges and tunnels and mountains and so on.
Right, right. That's inspirational, right?
Yes, yes. No, I really appreciate this overview, because you brought together so many things, and that's important that you don't overlook, you know, but that you have a more complete picture. So great, great. I'm really happy. Now,
thank you so much. Yeah.
My pleasure. Any more questions? Jacopo, I can see you. Or Jacopo, sorry. Yeah.
Jacopo is there. Okay, let me see who is there. Now I can look at the full picture of who is there. Maybe we can stop recording. Is that okay?
Yeah, we can stop recording if you want. Yes, fine.
Yeah, that way we can talk a little bit more informally. I can
no
say
problem.
Jacopo.
We usually record the questions, but if you wish, I can stop.
Okay. Okay, let's see the question then. I see Adam's hand is raised. So let's see the questions.
Yeah, I have one quite general question. What is known about this, let's call it hyperspace of all possible spectral triple with respect to this quantum Gromov-Hausdorff distance?
That's a good point. It's complete, and I don't know much else than that.
But is there any interest in investigating this whole big space, or?
No, that is a really good question. Definitely. I mean, I think it's a very good question. I maybe, you know, pass the question to Frederic, and if I have anything to share, I will do it via email. No, it's a definitely, you know, it's a great questions, but I don't really know much about that. He's the expert, really. Too bad I couldn't attend today, but but you know, definitely very, very interesting question. Yeah, it's
Okay, Tomek,
Tomek.
but unmute yourself.
Oh, yeah. I cannot answer a mute
Hello
question.
again.
That's too difficult.
I have a question, the following question. You said that you have parallel theory for distance between, let's say, non-commutative spaces, and also distance between their groups
Right.
of isometries.
Yeah. I showed you
suppose
the
that-
idea. Of
Yes.
course, there is more details in Frédéric's paper, but I showed you the idea. Yeah.
I suppose that you can combine this into some equivariant notion of distance between actions.
Yes, that's what we did in that paper in the isometry group. Of course, it doesn't have to be the isometry group that acts, but in that case, we were interested in the isometry group acting. Yes. Yes, that is in that paper with Bassi, maybe Jacopo. Yeah. Yeah. That's what we did in that paper. But there could be, that's a good point. There definitely could be other situations. In fact, I was thinking, we were talking yesterday with Frédéric, and we were saying, well, we didn't even consider this case in the case of the collapse. We didn't consider the isometry groups in the case of the collapse. Well, no, we didn't. It could be there is a hidden result there. So definitely there could be results in other areas, coming from this type of construction that we had not considered. I mean, it's, yeah, there could be definitely interesting results by using that idea of combining the two, definitely.
Yeah. So if you think about dynamical systems, so they are always similar to actions of groups of isometries or metric spaces. But if you think about collapses, such
Right.
problems like this, they are not present in such kind of phenomena. But they are very ubiquitous on the level of conformal actions, and then you obtain the phenomenon which is called bubbling. You can in the limit you can have some additional components bubbling one from another. So the question Adam asked is about the hyperspace of such things, and if you try to understand them as dynamical systems, then if you are interested in this collapsing, in this bubbling phenomena, which are very important in algebraic topology, for instance, even in the classical case.
That sounds very interesting.
Yeah.
That sounds very interesting. Are you planning to come again here, for in the summer?
I don't know yet. Maybe.
Well, if you are, we could, we could talk about this. As I said, I can ask Frédéric. I don't really know that much about this space and what you can say about the actions on this space and so on. But I'll be happy to send both you and Adam an email, and if he doesn't have anything to say, I can always say, he hasn't thought about the problem. I just don't know. I have not thought personally about that specific. I think it's an interesting space and it's an interesting question. I just don't know. I mean, I haven't thought about it and I couldn't even start to speculate. That's all.
So the motivation for my question is, of course, the question of Adam and also the name Fukaya.
Right.
I don't know if it is the same Fukaya.
It's a famous
It's
Fukaya.
in Fukaya category.
I don't know if it's the category person, but it's definitely a famous Fukaya. I don't remember his first name, but
the same Fukaya about symplectic geometry, topology, symplectic topology.
I'm sorry, I don't know. I know he's done lots of results on these. You know, if you look at stuff by Grove, other people, differential geometers, they have done a lot of collapse, but I don't really know. I can find out. I didn't put it in my references, but I could definitely find out the name of Fukaya, the first name of Fukaya. Let me see here. So can we shut the taping, please? I you know, for this more informal type of questioning, I prefer the recording is off.
Mm-hmm. Yeah, let's finish the formal questions and then we can discuss more freely. In fact, I have a quick question to Tomek because I'm really fond of dynamical systems, and we've been working with Mariusz Topolsky and others very strongly on a lot. I mean, working a lot on the concept of a dimension of an action. And I was wondering, so Tomek, it's a kind of crazy pseudo question for you. Do you think that you would have a result that if the distance between two actions is 0, then they have the same dimension? Like Rocklin dimension?
Probably not, because the question of the dimension is more subtle. It's about this system of it's a decomposition of unity. It's something not so related with metric.
Okay, good. So we can discuss it later. Anybody else who wants to ask a question to CARLA?
Okay, it's Ludwig. Hi, CARLA.
Oh,
Can you hear
hi.
me? So
How
just
are you?
well, thank you. Can you
Good,
see me? I
good.
don't.
Yeah, we see you. We see you. We hear you. Yes.
Yeah.
Okay. So I have various questions, but let's the simplest one is
Well, I mean,
remember.
at some point I need to go to teach, so let's not
Yeah,
make
so very
you know.
fast.
Okay.
I think in the Schwiger and Wagner, they already considered metric spectral triples or just spectral triples. I don't remember.
No, just spectral triples.
Oh, you
The
did
metric
this, okay.
part we
So
added.
if you have on the basis and on the group, then it's on the total space also metric. So 2 of 3, then the third one is also a metric, probably spectral triple, correct? Is it true?
Well, we haven't done the 2 or 3, you know, we just proven if the one on the bottom is metric, then the one on the top is metric.
Okay, providing that the
That's
action
what
is free,
we did.
or any action.
But there's probably some more results that one can finesse out of it. We just prove what we needed.
Okay,
That's
another question, quite general. So if spectral triple is not metric, what's wrong? You cannot do anything with it?
You cannot do the La Tremolière theory.
Okay.
I mean, it could be you could do other things. That's why we've been kind of stuck, you know, in this question of can we generalize it to this kind of, you know, splittings and factorizations of KK classes, because we couldn't quite put it in the framework that we needed, the Frédéric La Tremolière framework. So unfortunately, there is lots of technicalities and they are not all easy to pass through in a talk. But when we tried, I mean, I don't mean it's impossible, but our first try was actually to try to do it at the level of those factorization in KK elements and so on. But without having all of this framework of La Tremolière, we were stuck. But it doesn't mean it cannot be done or anything. It just, we couldn't do it.
Okay. Okay, thank you. Thank you, CARLA.
Anybody else? Andrzej?
No, thanks.
Okay, you guys? All right, so let me, Richard, how about you?
I'm okay.
No, okay. So let me finish by 2 quick comments and wind it up. So first, I did do the homework Carla told me to do, and I found the answer to my question about Bogoliubov automorphisms And you're absolutely right. I Googled up, and because I'm a DIMPAN, I could download it. There's a beautiful paper by Roberto Conti and Stefano Rossi about groups of isometries of the Kunz algebras, and I found the definition of a Bogolyubov automorphism. But I'm a bit puzzled because I found also a book of Neshviev and Erlich Stormer, which is a whole big book. And has a whole big chapter about Bogolyubov automorphisms, but in a different context. So I was just puzzled by the name Bogolyubov because it's something we would think about quantum field theory, you know, physics, yeah. But then
that's true. That's true, Piotr. This is generally associated with some transformation of the canonical commutation relations.
Before that,
exactly. And this is how it is in this book. So I cannot relate these two pictures, but it's a big subject. So
it's the same, Piotr, it's the same automorphisms.
The same, okay.
Yes.
Oh, good. That's just implementation by unitaries. That's the main idea, but very special unitaries.
Very special, because implementation by unitary is part of the definition, so definitely that's neat.
Yeah. I mean, you have this Kunz results, Kunz-Takesaki, I don't remember, that basically every automorphism of a Kunz algebra is implemented by a unitary in the Kunz algebra. And if you go to fixed point subalgebra and then to a very special part of it, and then take a unitary, this is Bogolyubov automorphism. So that's the answer to my question. Okay, and my second comment is that, CARLA is the node coordinator of Boulder. So anybody who is in the network, so Richard, Jacopo, Tomek, Andrzej, and I already did it, you guys, we can all go to CARLA and have the money. So,
if you come with your own money, please come,
Exactly. So many people who are here at the seminar can actually really go to CARLA. So that's absolutely feasible. Okay.
Right.
So let's thank CARLA again. This was a lot of joy for us. Thank you.
Sure.
And now I stop recording.
Okay. Sounds good. I found out that